viewers, feel most welcome into this channel, as here we are going to discuss our example whereby you can be told to find the Laplace transform of our function f of t is equals to t exponential 4t. What you need to understand is how to apply the first principle formula. When it comes to the first principle, the first thing that we need to understand is the first principle formula. And by the first principle formula, we know that the Laplace transform of our function f of t is equals to integration with respect to our limits exponential negative st, which is equals to a decaying function we multiply by our function f of t, and our integration is with respect to dt. Up to this point, we come and replace our function f of t with what it has been equated with on the other side, whereby we can come and say the Laplace transform of our function f of t is equals to t exponential 4t, which is equals to integration with respect to our limits exponential negative st we multiply by t exponential 4t, and our integration is with respect to dt. When you check at our integral here, the functions that we are supposed to be integrating, you will find that we are going to have 2 exponential. And when it comes to the 2 exponential, we need to reduce the number of exponentials. Here we are going to use now the laws of indices, whereby in the laws of indices, when the bases are equal, when the bases are same, we take one of the bases, but since it is a multiplication, we are going to add the powers. And this is what I mean. The Laplace transform of our function f of t, which we still know is equals to t exponential 4t, is going to be equals to integration with respect to our limits. Here we are going to have t exponential, we take one of the bases using the laws of indices, negative s, since it is a multiplication, we add the powers, and we are going to factor out our term of t because we have t here and we have t here. Our integration is with respect to dt. At this point now, we need to check the best way by which we can simplify our functions here. And when you check here, we cannot convert t into an exponential, and that one automatically will lead us into integration by parts formula, whereby integration by parts, we understand that the formula of integration by parts, we understand that an integral of u dv with respect to dt is equals to uv, we subtract from an integral of v du with respect to dt. But here it is an integration with respect to our limits. We must include the limits. Here the lower class limit, the upper class limit, the lower class limit, and the upper class limit. Before taking our integration, we need to put into consideration how we are going to have our u and dv with respect to d. We must use this acronym, whereby e here represents the exponential function. Here we are going to have the trigonometric function. Here the algebraic functions. Here the inverse functions. Here we are going to have the logarithmic. Functions. When we come here, you will find that we have t, which will be an algebraic because it is a letter. Algebraic function. And here automatically we are going to have our exponential. When we check our algebra, it comes first before our term of exponential. Our u, we understand we are going to have u is equals to t. Our dv with respect to dt, we are going to have dv with respect to dt is going to be equals to exponential negative s, we add to 4t. Our du with respect to dt is going to be equals to 1 because we differentiate our term of t, and our v is going to be equals to exponential negative s, we add to 4t all over negative s, we add to 4. When we check at here, we've worked out all the parameters that we need to insert in our integration by parts formula, whereby we can come and say now the Laplace transform of our function f of t is going to be equals to u. Our u is equals to t. We multiply by v. Our v is equals to exponential negative s, we add to 4t all over negative s, we add to 4. We come and have our limits. We insert our limits here. We subtract from here. We are going to have an integration with respect to our limits. Our v is equals to exponential negative s, we add to 4t all over negative s, we add to 4. We multiply by du with respect to dt. Du with respect to dt is equals to 1. And here our integration is with respect to dt. Let us work out this bracket by inserting our limits, whereby we are going to have the Laplace transform of our function f of t is going to be equals to, where we are having our term of t, we are going to replace with the upper class limit, and when we will be inserting our lower class limit, where we are having t, we are going to insert 0 before getting into the other side. So let us simplify our bracket here, and we are going to have infinity for this one, exponential negative s, we add to 4. We come and insert our infinity all over negative s, we add to 4. This is our first bracket. We subtract from here. We are going to have our lower class limit 0, exponential negative s, we add to 4. Our term of t, we are going to insert there our limit, everything all over negative s, we add to 4. We subtract from here. We are going to factor out 1 all over negative s, we add to 4. And here we are going to have, we multiply by an integral of exponential negative s, we add to 4t. Infinity multiplied by everything in this bracket. Here we are going to have 0. Here we are going to have 0. To mean that we are going to be left by the Laplace transform of our function f of t is going to be equals to negative 1 all over negative s, we add to 4. We multiply by our integration here. When we integrate our exponential here, we are going to have negative. Here we are going to have exponential negative s we add to 4 t all over negative s we add to 4. And our integration is with respect to our limit. That is the upper class limit and the lower class limit. Let us work out with our limits here, and we are going to have negative 1 all over negative s we add to 4. We multiply by 1 all over negative s we add to 4. We factor out this one, we come and multiply by exponential negative s we add to 4. We insert our upper class limit, which is the infinity. We subtract from exponential negative s we add to 4. We insert our lower class limit, which is equals to 0. The Laplace transform of our function f of t is going to be equals to, here we are going to have negative 1 all over negative s we add to 4. We multiply by 1 all over negative s we add to 4. And everything we come and multiply by, here we are going to have 0. We subtract from 1. Because exponential raised to a power of an infinity is equals to 0. Exponential raised to a power of 0 is equals to 1. Negative 1, this 0 does not have an effect. Negative 1 multiplied by whatever we are having here, automatically we are going to do away with the negative sign. It is going to be a positive. At this point now, on the numerator, we are going to have 1 all over. The denominator here, we are going to have negative multiplied by this one, negative of s, we are going to have s squared. We are opening our bracket here. Negative s multiplied by positive 4, we are going to have negative 4s. Negative positive multiplied by a negative of s, we are going to have a negative of 4s. And here now we are going to have an additional of 16. Let us now simplify our denominator here, and now we are going to have, here now we are going to have the Laplace transform of our function f of t is going to be equals to 1 all over. Here we are going to have s squared. We subtract from 8s, we add to 16. And this is now our answer. This is how you go about finding the Laplace transform of our function. F of t is equals to t, we multiply by an exponential of 4t using the first principle. This is how you go about it using the first principle. Let us now meet in my second example. This is now our second example, whereby you can be told find the Laplace transform of our function f of t is equals to t cos 5t using the first principle formula. And we understand that by using the first principle formula, the first thing that we need to understand how to write is the first principle formula. Once you've mastered how to write the first principle formula, the second thing is how we are going to use the first principle formula in simplifying our Laplacian function given. After that, you check, are we going to apply the integration by parts formula, or are we going to convert our trigonometric function into an exponential? Now from there, you just proceed with everything mathematically up to the last part. And that is what I'm going to take you through now. Here, the first thing that we agreed on is how to notate the first principle formula. When it comes to the first principle formula, we understand the Laplace transform of our function f of t is equals to integration with respect to our limits exponential negative st, and here we multiply by our function f of t. Our integration is with respect to dt. From this point, our function f of t is equals to t cos 5t, to mean that we are going to have the Laplace transform of our function t cos 5t is equals to integration with respect to our limits exponential negative st, we multiply by our function f of t, t cos 5t, and our integration is with respect to dt. This is now our function f of t. Up to this point, when you check here, we have cos 5t, and here we have our function t, to mean that we need, the first thing that we need to understand is that whether here it is a sine, a cos, sine hyperbolic, cos hyperbolic, you need to find a way by which you can change the hyperbolic functions or the trigonometric functions into an exponential. After doing that, you carry out your integration by parts formula because of our term, because of our algebra. Now let us start by changing cos 5t into an exponential, whereby we say that exponential 5tj is equals to cos 5t. We add to j sine 5t. Cos is located on the real side, to mean we are going to have r exponential 5tj is equals to r cos 5t, or I, to stand for the I exponential 5tj is equals to j sine 5t. This one stands for the imaginary, but when you check here, we have our cos 5t. We stand for the real side, to mean that we are not going to use this side and we are going to take the side of cos. We've only changed cos 5t into an exponential. Let us now get back into our working. The Laplace transform of our function f of t is going to be equals to integration with respect to our limits exponential negative st, we multiply by t cos, we are going to have r exponential 5tj, and our integration is with respect to dt. Up to this point, you'll find that now we have our two exponential, we have our r. We are going to factor out our r because it is not a term of dt, and we are going to reduce the number of exponential by using the laws of indices, whereby when the bases are the same, we take one of the bases, but since it is a multiplication, we are going to add the powers, and this is what we are going to have. The Laplace transform of our function f of t is going to be equals to r, we factor it out because it is not a term of dt. T, we just leave it there. Exponential, by using the laws of indices. Negative s, we add to 5j, we factor out t because it is a common term here, and our integration is with respect to dt. At this point now, we can do our integration, and we are going to use integration by parts formula, whereby I've discussed on how you are going to select your u and your dv dt. Here, we understand that integration by parts formula, we are going to have u dv with respect to dt. Our integration is equals to uv, we subtract from an integral with we subtract from an integral of v du with respect to dt. But here our integration is with respect to our limits. And here also we are having our limits. Let us now have our terms of u and our term of dv with respect to dt. Our u is going to be equals to t. Our dv with respect to dt is going to be equals to exponential negative s, we add to 5j t. To our term of u, we are going to do our differentiation. And here we are going to have 1. To our term of v, we are going to do our integration, and we are going to have exponential negative s, we add to 5j t, everything all over negative s, we add to 5j, just like that. From this point now, we are going directly into our formula because we have all the parameters that we need to go about integration by parts formula. Here now we are going to have the Laplace transform of our function f of t is equals to u. Our u is equals to t. Our v is equals to exponential negative s, we add to 5j t all over negative s, we add to 5j. Everything we come and insert our limits. We subtract from here, we are going to have integration with respect to our limits. V, our term of v, we are going to have exponential negative s, we add to 5j all over negative s, we add to 5j. du with respect to dt is equals to 1. Here we are going to have 1. But when you check here, it was r. We multiply by everything to mean that at this point now, I'm supposed to be having the Laplace transform of our function f of t is equals to r. Don't forget about the r that is here because we are doing integration by parts of our integral here. At this point, we agreed that when we insert your upper class limit into the term of t, we are going to have 0. And when you insert our lower class limit to the term of t here and here, we are going to have 0. Hence, this bracket is going to cancel out. And we are going to have now the Laplace transform of our function f of t is going to be equals to r into a negative of 1 all over negative s, we add to 5j. Here we come and factor out our denominator we multiply by this negative, we multiply by an integral of exponential negative s, we add to 5 j t. When we integrate here our exponential, we are going to have the Laplace transform of our function f of t is equals to r into negative 1 all over negative s, we add to 5 j, we multiply by an integral of exponential negative s, we add to 5j t all over negative s, we add to 5j, and our integration is with respect to our limits. At this point, we can factor out our denominator here and insert our class limit, whereby we are going to have the Laplace transform of our function f of t is going to be equals to r into negative 1 all over negative s, we add to 5j, we come and multiply by 1 all over negative 5, we add to 5j, and lastly we are going to insert our limit, whereby we are going to have exponential negative s, we add to 5j, our term of t, we insert our upper class limit, we subtract from exponential negative s, we add to 5j, we multiply by the lower class limit to the term of t after inserting. Here we agree that anything raised to a power of an infinity is going to be a 0, and here we are going to have exponential raised to a power of 0 is going to be a negative of 1. From this point now, we are going to have the Laplace transform of our function f of t is going to be equals to r into negative 1 all over negative s, we add to 5j, we come and multiply by 1 all over negative s, we add to 5j, we come and multiply by, here we said we are going to have 0, we subtract from 1, to mean that here now we are going to have a negative of 1. Negative multiplied by a negative, we are going to have our positive to the numerator. The negatives are going to cancel out. Here now we can come and multiply, we can come and open our brackets here by multiplying the denominators together. And we are going to have the Laplace transform of our function f of t is going to be equals to r into 1 all over negative s multiplied by negative s, we are going to have s squared. Negative s multiplied by positive 5j, we are going to have a negative of 5j s. Here we are going to have a negative of 5j s. And here we are going to have a positive of 25j squared. Let us now do away with our j squared here, whereby we understand from the complex numbers j squared is equals to a negative of 1. When we replace j squared with a negative of 1 here, this negative is going to affect our positive here, because when you take a negative, you multiply by a positive, we are going to have a negative, and automatically this one is going to cancel out. At this point now, we can separate the real functions and the imaginary functions, whereby we are going to have the Laplace transform of our function f of t is going to be equals to r into 1 all over s squared, we subtract from 25. Here we are going to have a negative of 10 10sj. These are our real functions. Up to this point now, we want to have the real functions and the imaginary functions together. For us to have the real functions and the imaginary functions, we must do our rationalization. By rationalization, we are going to multiply both the numerator and the denominator by conjugate of our denominator here. And this is what I mean. We are going to have now s squared, we subtract from 25, we add to 10sj all over negative s squared, we subtract from 25, we add to 10sj. Because this is a negative, when we are multiplying by the conjugate of our denominator here, at this point we are going to have our positive functions. Now, let us have a multiplication of our brackets here on the denominator and on the numerator. On the numerator, we are going to have the Laplace transform of our function f of t is going to be equals to r into, we are going to have s squared, we subtract from 25, we add to 10sj, and on our denominator we are going to have, for us to simplify our denominator here, we need to understand that when we have a plus b, we multiply by a minus b. A multiplied by a, we are going to have a squared. A multiplied by a negative of b, we are going to have negative ab. Here we are going to have positive ab. Here we are going to have negative b squared. These two are going to cancel out and we are going to have a squared. We add to, we subtract from b squared as our function. We come and treat our real function here as a, the imaginary as b. Here our real functions are as a. Here we are going to have the imaginary function as b. When you check out these two brackets here, we are having a negative bracket and a positive bracket. To mean our answer was equals to s squared, we subtract from 25. This one is our term of a. Everything is going to be squared, we subtract from b. Our b squared, we are going to have 10sj. Everything squared, because that is our b. Here on our denominator, we are going to have, in our denominator here, we are going to have the Laplace transform of our function f of t is going to be equals to s squared, we subtract from 25, we add to 10sj all over s squared, we subtract from 25, everything squared, we subtract from, here we are going to have 100 because of 10 squared, s squared, and here we are going to have j squared. But what do we know from the complex number formula? We understand that j squared is equals to, here we're supposed to be having our r, j squared is equals to -1. When j squared is equals to -1, here we are going to replace with a negative of 1. Negative here multiplied by this negative, we are going to have our positive sign at this point. And this is what we are going to have on our denominator. Now, at this point now, we can separate the real functions and the imaginary function. And this is what we are going to have. The Laplace transform of our function f of t is going to be equals to r into s squared we subtract from 25 all over s squared we subtract from 25. Everything will be squared. We add to 100 s squared. We come and add to 10 sj all over s squared we subtract from 25. Everything will be squared. We add to 100 s squared. At this point now, we've separated the real functions and the imaginary functions. But since here we were having our r, we are going to cancel out the imaginary function, and we are going to have our answer as the Laplace transform of our function f of t, which was equals to t cos 5t, is going to be equals to s squared we subtract from 25 all over s squared we subtract from 25. Everything will be squared. We come and add to 100 s squared now. And this is how you go about finding the Laplace transform of our function f of t is equals to t cos 5t using the first principle formula. Let us now get into our third example.